Welcome back to Applied Mathematics. In this video, I want to talk about some applications of similar triangles. You can see that there is a wall of text behind me, so let's not waste any time, get my head out of the way, and let's read through this, figure out what we are looking at. A surveyor is using line of sight to measure the height of a tree. Looking through a viewfinder set on a tripod 5 feet above the ground, she positions an 8-foot tall reference mark so that the top of the reference appears to be in line with the top of the tree. And I should let you know that there is a picture below this wall of text to try to make a little bit more sense of that. She then measures. The reference mark was placed 2.28 feet away from the viewfinder. If the viewfinder is itself 15 feet away from the base of the tree, how tall is the tree? And again, terrible sketch to go along with that. We have the person looking through the viewfinder depicted as an eyeball side on. We have the viewfinder itself depicted as a bit of a wedge. We have the reference mark 8 feet tall, 2.28 feet away. It looks kind of like a trident, but close enough. And then we have a tree that might look a little bit more like a lollipop, but again, close enough. And so, if the picture is given to you, that is always fantastic. If the picture is not given to you, I always encourage drawing a picture. If anything about the problem you're trying to solve is visual, draw a picture. It always helps, even if your picture is terrible, like this one. The next thing we want to do is try to find a strategy that we can use to solve the problem. And sure, this is the video on solving problems using similar triangles, so I'm probably going to use that strategy, but let's look a little bit at this situation and see if we can figure out why that is a useful strategy. To me, the thing that jumps out about this, first of all, is that we have a bunch of geometric measurements in a bit of a strange configuration. The next thing that jumps out at me is that we have some parallel lines. I think it is safe to assume that my reference mark is entirely vertical and that my tree is entirely vertical. Even if the tree is not vertical, we're trying to measure its vertical height. So, if the tree is at an angle, we're still measuring the vertical height, not the length of the trunk. And so because we have those parallel lines, angles in corresponding position have equal measure, so there's a couple of equal angles. And as soon as I start talking about equal angles, I get excited thinking about triangles. Although this is not a triangle at the moment, is it? We're going to have to do something about that. And so I'm going to draw in one more line. I'm going to draw that line in along the ground so that the height of the viewfinder is 5, but that viewfinder is on the triangle. And then similarly, that line is going to cut 5 feet above the ground on my reference mark and 5 feet above the ground on my tree, leaving me with a nice triangle. I'll also point out here that the way I drew this, it looks like I have a right triangle, which would be really nice, but I don't actually know that. This is an online class. You could be taking this anywhere, but I live in southwestern Pennsylvania, where finding 15 feet of level ground is nearly impossible. So, even though I drew this as flat ground, chances are very good that it is at some angle. And so I don't have a right angle at this side. And so I'm not going to use that as something known. I'm not going to try to take advantage of that in my calculations. I'm just going to use the fact that I have some equal angles here. And even if they aren't right angles, they're going to be equal angles here because, again, two parallel lines cut by a transversal. So angles in corresponding position have equal measure. That's enough information to tell me that these triangles are similar. And now that I know that the triangles are similar, I can start solving the problem. I've got a smaller triangle which measures 2.28 feet on this side. And then the other leg of the triangle, not the long side, the shortest side, the way that I've drawn it here, although it's actually not drawn to scale, as we'll see in just a moment, because the distance here is the distance in this part of the reference stake, which is the part above this 5 feet. The entire stake is 8 feet tall. 5 feet are already accounted for. 8 minus 5 is 3. So the rest of this triangle is 3.00 feet. I don't know what the third side of the triangle is, and I don't need it, so I'm not worried. Instead, I'm going to jump immediately to the larger triangle. I'm going to realize that this side down here is 15.00 feet. And this side over here, again, here's where things get a little bit interesting. The height of the tree is x, but my triangle starts 5 feet up. So this side of the triangle is x minus 5. Right, that drawing the triangle 5 feet off the ground makes things tricky. But we can handle it. It's something that we can do. I'll also be honest, I chose this problem because it's about the trickiest one I could come up with. If you can follow this, then problems in homework should be really easy by comparison. All right, but these two triangles are equal. And because these triangles are equal, corresponding sides have to have lengths that are in proportion to each other. So on the smaller triangle, I have the sides measuring 3.00 feet and 2.28 feet. And everything is in feet, so the feet are all going to cancel each other out. I don't even need to have written them in the first place. On the second triangle, the side that corresponds to 3.00 feet is the side measured x minus 5. And I guess that should be 5.00. I was lazy when I drew the diagram because I didn't quite have enough room for everything. And then the side that corresponds to the 2.28, the side along the bottom, is 15.00. Again, numerator and denominator in feet. Feet are going to cancel out. I know I'm going to be left with x in feet. I don't need to carry the units along with me. Now that we've done that, we've set this up as a proportion, we can solve the proportion. We don't need the picture anymore. But we're going to have 3.00 times 15.00 is equal to 2.28 times x minus 5.00. And be careful, make sure you distribute over there on the right-hand side. 3.00 times 15.00 is 45.0. Then I'm going to have 2.28x, and let's see, 2.28 times 5. My calculator tells me is 11.4. Add 11.4 to both sides. And then divide by 2.28. round to 3 significant figures, and I get 24.7 feet as the value of x. Right. I took into account the fact that the triangle started 5 feet above the tree, so that is in fact my final result. This tree is 24.7 feet tall. That was, as I said, a fairly involved problem. It took some thinking, it took some creativity to set it up. Hopefully it all makes sense to you. I think that that's enough for this video, so I'll wrap up here. As always, thank you for joining me. I'll see you next time.